last class we started discussing conductors, and conductors are mainly used to conduct electricity, because conductors as opposed to dielectrics have a lot of free electrons. As we discussed in the last class, conductors have an abundance of free electrons because their conduction band overlaps with that of the valence band. Most conductors such as aluminum, copper, silver, they have so much of free electrons, free electrons in the sense that they are very loosely attached to the lattice, that a small amount of electric field that we could apply would then give enough force, or it would accelerate the charges enough such that these charges would start moving and constitute a current. The force on each electron inside that of a conductor is given by the electric field acting on the conductor at that point, and it is given by minus q E, where E is the electric field and Q is the charge on the electron, and this minus sign indicates that the electrons would actually move opposite to the electric field. Okay. So, while the electric field, for example, is along the x axis, then the movement of the electrons to that electric field would be opposite to that of the x axis. However, a positive charge such as a hole in a semiconductor would move along the direction of the electric field. So, conventionally the direction of electric field lines would represent the actual direction of a positively charged particle. Since electrons are negative, they would move opposite. It turns out that the velocity with which these electrons move is called as a drift velocity, is actually proportional to the electric field. Okay. So, the drift velocity is related to the electric field by a quantity called mobility. Mobility tells us how mobile a charge is, in the sense that how easy is that charge would start to move when an electric field is applied. Okay. Compared to holes, which you would read in the semiconductor device physics courses, the mobility of electrons is much higher. In fact, the difference between the mobilities of holes and electrons is what makes the speed of the devices such as MOSFETs be capped off. In other words, there is a limit in the speed because the holes move at a much slower speed compared to the electrons. Okay. And one can actually use this drift velocity, substitute this in the expression for the current density. We know that the current density is related to the electric field as the velocity charge density rho v times electric field. Okay. And you can see that this charge density at any point will be given by n q mu. I am writing this for the case of an electron, and I am not really using the minus sign. You just have to remember that electrons move against the field, and however their current would actually be considered in the direction opposite to the electron movement. So, the conventional current flows from left to right, for example, as the electrons would move from right to left. Okay. So, I am not writing the minus sign, but you have to mentally understand that the quantities would be negative wherever appropriate. Okay. So, when you are considering electron flow, you have to use the appropriate minus signs here. Okay. So, the current density J is related to the electric field by this expression, okay, where the charge density is given by, this is rho into V, yeah. So, this is rho V. So, charge n is the number of electrons per unit volume, q is the charge, therefore, this corresponds to charge per unit volume, and mu being the mobility of the electron would tell how quickly or how fast this electron is moving. Okay. In common language, this n q mu, okay, is given by a quantity or is represented by a quantity called sigma, and sigma stands for conductivity. Okay. Sigma stands for conductivity, and in olden days it was measured in 1 by ohms, or sometimes called as mhos. Okay. The modern unit for measurement of conductivity is that of a Siemens. Okay. So, conductivity is measured in Siemens, but these are sometimes also measured in terms of Siemens per meter. Okay. So, conductivity or conductance is measured in Siemens, and sometimes they are also measured in Siemens per meter when you are considering the appropriate quantities over here. Okay. Or Siemens, let us just say, and S stands for Siemens. Okay. If you look at typical values of the conductivity of say copper, copper has conductivity of about 5.8 into 10 to the power 7, okay, and that of the silver is around 6.17 into 10 to the power 7. Note that these conductivities, although they are quite high, they are not really infinite, right. So, if you consider a metal or a perfect conductor as that having a value of sigma going to infinity, these are not perfect conductors. There is some amount of resistivity amongst these conductors. Resistivity is roughly inversely proportional to the conductivity. Okay. So, because sigma is not infinity, there is some amount of resistance. So, if you were to take a capacitor, which we will be discussing very shortly, and the capacitor plates are made up of this conductors of finite conductivity, what would happen is that as the voltage is applied, because the resistivity is not 0, there would be some amount of current flow that is happening inside the conductor itself, okay, leading to losses. These conductive losses become very important, especially at high frequencies, as we will see when we discuss transmission lines. Okay. Moreover, the conductivities that we have represented over here or given the values over here are not really constants. They are dependent on temperature, and for every 1 degree Kelvin or 1 Kelvin rise in the temperature, okay, for every 1 Kelvin rise in temperature, you will see that the conductivities would actually change by about 0.4%. Okay. In fact, this can be used as one of the temperature measurement, a very sensitive temperature measurement instruments. Okay. Now, let us develop one very important relationship between the voltage and the current of a conductor. Okay. Before we go further, let me remind you that J equals sigma E is a relationship that holds in most materials, although calculation of sigma is not really done by just giving n q mu, it requires quantum mechanics to properly give you the values. This equation or the result J equals sigma E looks so much like V equals I R or I equals G V that we call this J equals sigma E as Ohm's law. Okay. The proper or the more popular form of Ohm's law is that of the relation between voltage and current. We already know what is voltage, how do we represent voltage or how do we relate voltage to electric field. We remember that voltage was the potential difference between any two points, and this potential difference was the line integral of the electric field along any path. In the electrostatic case that we are considering, this line integral and hence the potential difference was independent of the paths, but V was related to the line integral of electric field. So, it is given by some 0.1 of the conductor to 0.2 of the conductor and electric field. Okay. So, this is how the voltage or the potential difference between 2 points is related. We also know how to relate current to J, because current is J into S. I am not writing the integral relationship, but the essential idea is that you take a surface which has to be open, not closed. Okay. So, you take a surface and how are the J field lines coming out of the surface and integrate those J fields over the surface, okay, because it could happen that the surface you are considering will be at an angle with respect to the J field lines. So, in that case what will happen is I will be equal to integral of J dot ds. However, if J and S are aligned perpendicularly in the sense that surface is perpendicular to the J field lines, then the current through that open surface will be equal to J into S. Okay. Consider this scenario in which I am considering a piece of conductor of certain length L. Okay. Of course, this must be a uniform conductor, but the drawing might not really represent this. Okay. So, I can say this is bad diagram, but represents uniform conductor, okay, conductor of uniform cross section. So, how do we calculate the voltage difference between the two? So, if you label these points as some point B and point A, the voltage difference between the points A and B is simply the line integral of the electric fields that is there inside this conducting material, okay, from point B to point A. So, you integrate the electric field inside this one, assuming dl points along this line from B to A, and whatever you do, you are going to get the corresponding potential difference. So, if the electric field and dl are aligned properly and if the electric field happens to be uniform over the piece of length that we have considered, then you can simply replace this by E into L. Okay. Whether B is at higher potential or A is at higher potential, you have to determine appropriately. For example, if this is a situation in which B has a higher potential, then the potential difference from B to A would be called as potential drop or voltage drop. Otherwise, A to B would be called, or B to A, if B is smaller and A is larger, it would be called as potential rise. Okay. In a typical circuit element of a resistor that we consider, we assume a potential drop and a current that is flowing in, right. So, if you assume that the current I is flowing in and the potential drop is V, the relationship between V and I is the resistance, or the ratio of V by I is the resistance. So, the potential difference or the potential drop, let us assume, is given by E into L, and the current I will be J into S, where S is the cross section of this open surface that you are looking at. So, if the J field lines are there, then the current through this piece of material will be J into S. Let us also assume that these quantities are uniform. Now, resistance, as we have just described, is given by the potential difference, which is E L, divided by the current through the conductor. The current through the conductor is J S. However, I also know that J is related to electric field, that is J is sigma times E from the field Ohm's law, right. So, from the field Ohm's law we have J equals sigma E. I can substitute that inside here to get sigma E into S in the denominator. Cancelling the electric fields from numerator and denominator gives me L by sigma S. Okay. This is a relationship that you must have seen quite earlier. This is the expression for the resistance of a wire which has a surface area of S, is made up of conductivity sigma, that is made up of conductor with a conductivity sigma, and has a total length of L, right. A uniform wire of cross section S, conductivity sigma, having a length L, will have a resistance of L by sigma S. Now, sigma is 1 by rho and rho is called resistivity. So, you can rewrite this equation as rho L by S, okay, and this will give you the resistance R. Of course, this is the resistance for a piece of conductor that we considered where everything was uniform. Okay. However, if you want to go to the general relationship between electric field and the current density and the resistance, you have to consider the potential difference between the two paths. So, line integral of the electric field between the two paths divided by the current that is coming out of the surface. Okay. So, this is the definition of resistance. One can actually think of this as the definition of resistance, and what is the important point about this definition is that the electric field could be non-uniform, okay, as well as J could be non-uniform, and in fact one can actually develop a point form of resistance. So, instead of calling a resistance as some as of a piece, one can also say resistance at every point. Okay. That leads to the concept of non-uniform and spatially varying resistances. Okay. Of course, in order to get these non-uniform and spatially varying resistances, you need the electric field and the J fields to be varying, or they be non-uniform as well. Okay. All right. So, let us close the discussion on conductors by looking at the boundary conditions. Okay. For now, let us look at boundary conditions for the D field and E field. We will not touch the boundary condition for the J field, because I want to keep the boundary condition for current when we have also discussed the magnetic fields. Okay. So, right now I do not want to clutter our boundary conditions by talking about J fields, although for a very simplified case you can see that J field has to be continuous across the surface. Okay. Now, before we talk about boundary conditions, here is something that we want to ask. Let us take a piece of metal, okay, or a piece of conductor, metal of course being a conductor, and let us place some charges inside. Okay. Let us place some charges in the body of the conductor. What do you expect to happen? Now, what happens is that these charges which are placed inside the conducting body would rearrange themselves or migrate in such a way that the charges would actually appear on the surface. Okay. Of course, as we have already discussed, it is not necessary that these are the same charges that would appear on the surface, right. So, we discussed this fact that when you take the current and the electrons are flowing, it is not necessarily that the first electron would be the one that is actually coming out of a particular piece of conductor that you are considering, right. what would happen is electrons would go to the next lattice, occupy the next available position. From that position it would kick out an electron, and this process would happen, something that we talked about in the analogy of traffic car, cars moving in a traffic. So, similarly here what would happen is, when we say that the charges get distributed, it is not necessarily that the original charges get distributed, the charges would go inside the lattice into the conductor, but they would essentially come out in the sense that they would actually be appearing on the surface, not necessarily the original ones, but the rearranged charges. Okay. From the point of view of an observer standing outside the conductor, what it simply means is that you take some charges, put it inside a metal, okay, you might probably want to dig a small hole through a drill and then place some charges inside and seal the hole, seal the hole, but what you would find is that these charges would not stay inside, but rather distribute distribute themselves in such a way that they would appear on the surface and contribute to the surface charge density. Okay. So, no charge which is placed inside the conductor body would remain there, and all the charges would appear on the surface. Okay. In such a way that these charges do not just appear randomly, okay. These charges would appear in such a way that there is no electric field inside the conductor. Okay. This is a very crucial result that you need to remember. Okay. Even a moderately conducting material would have very negligible amount of electric field. Okay. So, electric field inside this is a property of the conductor. One cannot really define this or derive this condition, it is essentially the nature of a conducting material. You might of course ask, how much time would it take for these charges which are placed inside to come or be visible on the surface, or they get distributed onto the surface, and this time is what is called as relaxation time. Okay. And relaxation time for charges is around 10 to the power minus 19 to 10 to the power minus 18 seconds. Okay. This relaxation time is so short that in a matter of less than attoseconds, that is 10 to the power minus 18 seconds, the charges would all be moved and would be placed on the surface. Again remember, it is not the original charges which are moving, okay, because you can calculate and see that the velocity required would be very high. It is the effective charge that appears on the outside. Okay. Now, when such a thing happens, right, if you go back to the metal, there are certain charges available on the surface. Okay. I am indicating only a few charges, but you should imagine that there is actually a layer of charges here. So, there is a surface charge layer that is surrounding, in the sense that they are just below the conducting surface. Of course, they cannot just leave the conductor. There is a very interesting reason why they cannot leave, but something that we will not be talking about it. Suffice to say that the conductors are, although we are drawing them as attaching on the outside of the surface, they are not leaving the surface, they are just below the conducting surface, okay, but they are essentially surface charges. Okay. They are occupying very small distances, but they are just below the conducting surfaces. Now, if you ask what is the electric field inside, obviously the electric field inside is 0. What is the D field inside? D field inside is also 0. Why? Consider this interior surface that I have drawn. Obviously, this surface does not enclose any charge. So, if you want to ask for what is the internal D field from Gauss's law, you see that dI dot ds over the interior surface Si will be equal to 0, okay, and this implies that dI will also be equal to 0. We also have seen that the E field is 0. Okay. Now, we are good to go with boundary condition. Consider free space or a dielectric, okay, and then consider one conductor here. Okay. We know that charges, if at all they are placed, they would be available on the surface of the conductor, forming a surface layer of charges. Okay. Now, to obtain the boundary condition for D and E, we follow the procedure that we adopted in the last class for dielectrics. So, you first imagine that there is a path here which has a certain width, okay, and a certain height. The path is traversed in a particular direction satisfying the right hand rule. The path has a height delta h and a width delta w. Okay. Now, apply the electric field, the line integral around this path. So, if you apply the line integral around this path, what you find is integral of E dot dl, right, which must be equal to 0, the line integral for this path that we have shown here will be E tangential in the conductor, okay, times delta W minus E tangential outside the conductor. So, let us call this as the free space tangential electric field times delta W plus some terms that would be multiplied by delta H, that is the normal components of the electric field multiplied by delta H. This entire thing will be equal to 0. As before, take the limit of delta H going to 0. If you take the limit of delta H going to 0, then these terms with delta H cancel and you are left with tangential electric field inside the conductor delta W minus tangential electric field with the free space delta W, that should be equal to 0. Of course, there cannot be any tangential electric field inside the material, inside the conductor. Why? Because if there was any tangential electric field, then it would start to move the charges. So, if charges movement is not considered electrostatics, and therefore, there will not be any tangential electric field, or this tangential field would move the charges in such a way that after a very short while, that is relaxation time, the charges are there in the equilibrium. Okay. So, the tangential electric field inside the conductor will be equal to 0, which simply means that tangential electric field just outside would also be equal to 0. Okay. So, the electric field tangential component both inside the conductor as well as on outside the conductor will be equal to 0, and this is the continuity for the tangential electric field. Now, to obtain the continuity condition for the tangential for the normal D field, we imagine writing a box, right. So, you can think of this as a kind of shape that we normally take. So, I still have some surface charges, okay. And now what happens? Now, I have two surfaces, the top surface and the bottom surface. Okay. The bottom surface is in the direction opposite to the top surface, that is the normals are not in the same direction, they are in the opposite direction. Outside, let us call this D field as D normal, because that is the only component that is necessary to consider in this particular scenario of the Pepsi can thing. So, D normal and in the free space, right. So, D normal free space, and the D field in the conductor will be D normal in the conductor. However, we have just shown that D field inside metal will actually be equal to 0, or a conductor will be equal to 0. This means that the normal D component inside the conductor will be equal to 0. So, this is actually equal to 0. So, if you leave this component out, what you have is D normal free space multiplied by whatever the surface area of this top surface that is there, that is let us say delta S. This must be equal to the total charge that I have here, right. So, that must be equal to volume charge density rho v delta S delta H, that should be the total charge that is contained. And of course, as delta H goes to 0, this becomes rho S, okay. And delta S on both sides will cancel with each other. This implies that the normal component in the free space, okay, and since this is the only component that would be available, because the normal component inside the conductor is 0, I can dispense off with all these free space ideas and say dN2, where 2 stands for free space, 1 stands for conductor. So, dN2 will be equal to rho S. Okay. So, this is the relationship for the normal component of the D field, and the tangential component of the D field is simply 0. So, E tangential is equal to 0. Okay. So, from this you can also find out what would be the normal component of the electric field. The normal component of the electric field will be rho S times whatever the epsilon of the free space is. If it is not free space dielectric, if it is a different dielectric, then you need to replace that rho S by epsilon, because D is epsilon times electric field. So, the normal component D will be equal to rho S, and normal component of the electric field En2 will be rho S by epsilon, right. So, this simply implies that En2 is equal to rho S by epsilon, where epsilon is that of the dielectric that surrounds the conductor. Okay. All right. Now, we summarize what we have learnt about the conductor. For a conductor, okay, let me write down these 3 points. Okay. Conductors have no internal fields, that is, have no electric fields inside. E is equal to 0. They also do not have D field. Okay. So, essentially they do not have any field inside that of the material. Okay. The fields, that is D fields or the electric fields, are always normal to conductor. Okay. The fields are always normal to the conductor. If there is any external field that is applied to the metal, it will induce charges on the conductor surface constituting a surface layer of charges rho s. Most importantly, because there is no electric field, it means that the potential of a given conductor is actually constant, and we call this as equipotential surface. We say that a conductor of an arbitrary shape is actually an example of an equipotential surface. Okay. So, please note that these conductors that we have considered have no electric fields or D fields, there are no fields inside. We also have seen that the fields are normal to the conductor. They also induce charges, or charges are induced on the conductor surface when they are immersed in external electric field, and these conductors are equipotential surfaces.